Hi everyone. Okay, so I'm working through the solutions to problem set 37, Moore-Gauss's law and electric potential. And I thought I'd talk through my rationale for the last couple of problems. Here's problem 4 to start. So the statement of the problem is there's two positive point charges. They have different charges and they're certain distance are not apart. They both have mass, and we hold the big charge at some fixed location in space and let the little charge move. Um, and we're interested in figuring out something with the speed of little q as it's pushed away by big Q. So we're assuming that they're like charges. There's three parts, A, B, and C. Considering the mechanics we've learned so far this year, what approach should we take if we're interested in finding the speed of little q as a function of time? What approach should we take if we're interested in finding the speed of q as a function of position? And see if q starts at rest, finds its speed once it is a distance 2 r naught from charge q. Okay, so let me pull up my iPad here and I can show you how I'm thinking about this problem. Okay, so here's kind of what the problem looks like. There's a big charge here with charge big Q and mass big M. There's another charge here, charge little q, mass little m. There's some distance r naught between them. So part A asks, what approach should we take to this problem if we want to figure out the speed of little q as a function of time? The approach we'd want to take here is to use Newton's laws. The reason for that is because Newton's laws say that the force on an object, the net force, is equal to the mass of that object times its acceleration. And as we discovered in the first semester, really this is a differential equation, but it's a differential equation in time because I can write the acceleration as dv dt. And so now I'm looking at the way that the velocity changes in time. And so if I'm interested in knowing something about how the velocity changes in time, Newton's laws are a great approach here. It's going to be really hard in this case, because if you think about the net force on this charge, the net force looks like the electric force, which is something like kqq over r squared r hat. So really what I need to do is to put that into a differential equation, which is going to be ugly to solve. Although if you think about it, it's really kind of the same thing as gravity, right? Because the electric force has the same form as gravity. So we should expect the solutions to a differential equation with Coulomb's law to look really similar to solutions with Newton's law of universal gravitation. So maybe we would predict sort of elliptical motion for little q, depending on its sort of initial velocity and what it's doing. But we don't have to solve this. It's just asking about what approach should we take if we want to find velocity as a function of time. So really we want to use sort of Newton's laws here. And I hope my rationale makes sense for why. That's part of the reason why I wanted to talk through it. In part B, that asks us, what approach should we take if you want to find the velocity of little q as a function of its position? In this case, Newton's laws maybe isn't the simplest approach because that will help us figure out, say, the velocity as a function of time. And from that, we could get the velocity as a function of position, but that's probably more work than we really need to do. So in this case, we really want to take an energy approach. Because as you may remember, what we do in an energy approach is typically we would say in a system like this, where only conservative forces are acting, then the change in total energy of the system is zero. And that's the same thing as saying that the change in the potential energy plus the change in kinetic energy is equal to zero. But we know that the kinetic energy, I can write this another way. Let me write it like this. So the initial energy and final energy are the same. That's the same thing as saying the change in energy is equal. which is the same thing as saying initial potential energy plus initial kinetic energy is equal to final potential plus final kinetic. Here we know the potential energy will depend only on the position of little q. That's what it means that the electric force is conservative. And we kind of know that form because we know the potential at any point where little q is due to big Q. It only depends on where little q is relative to big Q. So that's nice. And we know the kinetic energy really only depends on the speed. So this thing, I can say that these only depend on position. They don't depend on time at all. They also depend on, the charge of little q, the charge of big Q, but we'll leave it there for now. And the kinetic energy only depends on velocity. So these two things only depend on velocity. So if we're interested in figuring out how the velocity depends on position, this is a relationship that'll tell us something about that. So this general approach will get us where we need to go, which is kind of nice. Because in part C of this problem, part C asks us, what is the velocity of little q when it's 2r0 from big Q, from Q. So let's try that with an energy approach. So how do we use an energy approach here? Well, we can use what we know about potential. We know that the potential at some region near big Q, the potential as a function of position is equal to K big Q over R. That's what big Q does by itself. But we also know then that, and really as a reminder, what that means is it's the potential difference between infinity and the point R here. Then we know that we can also write the sort of potential function as a function of R for little q, just by multiplying by little q, because that's our definition of the difference between potential and potential energy. So the potential energy really just looks like this at any given point R. And as a reminder, really what that represents is the difference in potential energy between infinity and some point R. But whatever we take to be zero, it sort of comes out in the wash when we start doing our problems, because we're only ever comparing potentials between 2 points, as we'll do in our energy approach here. So how do we do this? Well, we can say that the energy is conserved as little q moves from r0 to 2r0. So let's say that our initial spot is r0 from q. So the potential at that spot is kqq over r0. The kinetic energy at that spot is 0 because we're releasing little q from rest. After little q gets to 2r0, the potential is kqq over 2r0. And the potential, or excuse me, the kinetic at that spot is just 1/2 little m v squared. I'll just leave it as v because that's the v that we're looking for. So if I put all this together using just sort of our normal energy approach, which I stated up here, then I can say that the initial energy is equal to the final energy. So let me scroll down a little bit. So then I know that the ui plus ki equals uf plus kf. And that says that kqq over r0 is equal to kqq over 2r0 plus 1/2 mv squared. I'm going to subtract this part to the other side. So if I take qq over R naught minus KQQ over 2 R naught, I just get KQQ over 2 R naught is equal to 1/2 mv squared. And then I just need to solve for v here. So I'm going to move, I can cancel this factor of 2 here. I'll divide by m and then take a square root so that I get that the square root of KQQ over m R naught equals v. And that's using an energy approach to figure out what the velocity would be to R naught away from big Q.